Okay.
Let's get to it. So I have quiz 4 to give back. I'll do that at the end of class. Someone remind me. I don't know if you guys noticed already, but also your report cards just changed because the 2 quiz grades being dropped took effect. So hopefully that bumped up a lot of you and put you on the right side of things. So far we've had 3 quizzes that count for your grade, and now 2 are dropped, so your quiz grade is your best quiz grade. So now if you got 100 on any one of the quizzes, your quiz grade is now 100. And so that will boost up a lot of people. And so if you continue to doing that well or better, your grade will only improve, whereas if you drop lower, it will get worse. So yeah, that's a good thing, I think. So overall, the class average just rose, and once we have more than 3 homeworks, there's going to be another bump for when 2 of those are dropped, just so you know. But let us continue. Last time, we spoke about something we called the derivative, which was our solution to the rate problem, and we derived the fact that's for a function f of x, for a special function, we can find something called f prime of x, which was the derivative of x, which was, what was the definition that we had here? Yeah.
The limit as h goes to 0 of f of x plus h minus f of x over h.
Okay. So it's the difference quotient, and we're taking a limit as the denominator goes to 0. So that gives us the derivative, and so what you can realize this is the slope of the function at x, or you can think of it as the slope of the tangent line to f at x. You can also think of it as the rate of change of f with respect to x. That is how fast the y value is changing in relation to the x value. So you can have a bunch of meanings here. This one is particularly useful a lot of the time. Mathematically, these 2 definitions are useful, but when you talk about applications, we will tend to think of this quantity as a rate of change or some sort of speed or velocity, which we will talk about some more. So we introduced that, which you would have to regurgitate on your quiz earlier today, and you'd actually have to use this. We showed an example where we actually used this to find the derivative of x squared and find the equation of a tangent line there, something that was again on your quiz. So today what we're going to do is I'm going to introduce some properties of the derivative, which are I'm going to first do some more examples of this because it's very important that you know how to do this. So we're going to do some more examples using this guy. Then we're going to talk about some algebraic properties of the derivative. Then we're going to talk about one of the derivative rules that can make finding derivatives easier. And we will continue that discussion on Friday. So for now, this is where we are. And so let's do some examples. So here's what we're going to do. Use limits to find f prime of x for the following. So first function that we're going to want to look at is f of x equals c, where c is a constant. Let's also look at f of x equals a constant times x. Again, c is a constant. C. Let's look at if we have the square root of x, what would its derivative look like? Let's look at the function 1 over x. What would its derivative look like? And we're going to finish off this set of examples with the sine function. What does sine of x, what does its derivative look like? And we're going to derive all these using the definition. So whenever, and this is going to be important, whenever a derivative problem says use limits, or we could say use the definition of the derivative, it's talking about using the limit definition, which means you're not allowed to use the shortcuts. You have to use the limit definition, where f prime is equal to the limit as h approaches 0, f of x plus h minus f of x over h. That's going to be a pretty important formula to memorize, and you will be required to use it. You had to do it in the quiz today. You will be required to use it on the first test and on the final as well. So that being said, let's actually just jump into it. Let's see what these guys give us here. So let's find f prime of c if our function is a constant. So we know the derivative is going to be given by the limit as h approaches 0 of f of x plus h minus f of x all over h. Again, keep writing down a formula until you have it burned into your brain. You have it fully memorized. Any guesses as to what the answer would be? Yeah?
0.
Why?
Because it's a constant, so slope is 0.
Slope, how do you know the slope is 0 if it's a constant?
Because if you're drawing, like graphically drawing it, it
Yeah.
would be like a straight line.
Right, it'll be a horizontal line,
Yeah.
right? Passing through C. We know the slope of a horizontal line is 0, so we expect to get 0 as the answer here. Let's actually see. So if f of x equals c, what is f of x plus h?
See.
It is also c. Remember what f of x plus h means? It means you go to the function, everywhere you see an x, you replace with x plus h. There are no x's, so nothing happens. It's just c. F of x, again, is c over h. So we end up with the limit as h approaches 0, of 0 over h, which is 0. So we can state this as a rule. From now on, it's something that you can just know right away. It'll make your life a lot easier. And using the other notation, which we also spoke about last time, we can state rules in shorthand using this notation. The derivative with respect to x of a constant is 0. And that's just something we know now. The derivative of any constant is 0. It does not matter what the constant is, the derivative would be 0. So the derivative of phi is 0. The derivative of pi is 0. The derivative of e is 0. The derivative of e raised to the pi minus radical 2 divided by 17.89 is 0. The derivative of a constant is 0. It doesn't matter how the constant looks, whether it's ugly or not. If there are no x's in the thing, the derivative is 0. Okay. So that's the very important thing to know. The derivative of any constant is 0 because a constant is just a horizontal line and the slope of a horizontal line is 0. Okay. So that's just something we know now, and we actually just proved that using the limit definition. Any questions here? Nothing much happened there. Let's try this one. Maybe it's a little more interesting. So what if we have a constant times x? So we know that the derivative should look like the limit as h approaches 0 of f of x plus h minus f of x over h. Keep writing it down until you remember the point. So what do you think the answer should be here? C, right? Again, using our interpretation as slope, right? C here is kind of like the slope of the line. It will be the mx plus b. You can think of this as a line where the b is 0. C happens to be the slope of the line, right? So this could be a 5x, we know the slope should be 5. If it's a 3x, the slope should be 3, etc. So expect the answer to be C. Let's see if it actually works out. C, if it actually works out. What would f of x plus h look like here? Yeah?
C times x plus h.
C times x plus h. whenever I see an x, I replace it with an x plus h, minus the original function, which is c times x, over h. So this is, of course, cx plus ch minus cx over h. This cancels that. And you'll also see that the h would cancel that, because now that's gone and it's just a product. So we have the limit as h approaches 0 of c. There is no h here, so that is just c. And therefore, we can talk about that as a rule. The derivative of a constant times x is just a constant. And that can just be something we know. In particular, if c equals 1, we find that this tells us the derivative of x is the number 1. Also something that is just nice to know right off the bat. So, example, the derivative of 3x, as I said, would be 3. The derivative of ex would be e. The derivative of 1 plus radical 2 over 3 divided by pi raised to the e power times x is 1 plus radical 2 over 3 over pi raised to the e. Whatever the constant is multiplying the x, I don't care how ugly it looks. If it's a constant, the derivative is the constant. So the derivative of constant times x, the derivative is just the coefficient. Moving on. So that was b. Let's look at radicals. In particular, the square root. Let's look at the square root of x. Now I want to find the derivative. How would we do it? We take the limit as h approaches 0 of f of x plus h minus f of x all over h. What does f of x plus h look like here? Yeah?
Radical x plus h.
Radical x plus h?
No, the radical would be
Right, radical x plus h. You replace that entire x with x plus h minus radical x all over h. How do you simplify that? Yeah? Yes?
Could you multiply the top and bottom both by the square root of x plus h plus root x?
Right, multiply and divide by the conjugate. This is one of the algebra techniques we have for simplifying this. So you want to rationalize the numerator is the trick. So we multiply by x plus h plus radical x divided by x plus h plus radical x. Multiply and divide by the same things like multiply by 1. We're not changing the values. It will just make it more convenient to look at. In the top, now we realize this looks like a minus b times a plus b. Therefore, we get a squared minus b squared. And we still have the limit here. In the denominator, I just have h times that whole thing. Remember, we never expand the denominator, so I'm just going to leave it like that. The x's would kill each other because you have x minus x. The h's would also cancel because now there is a product in the numerator. And so we're left with the limit as h approaches 0 of 1 over radical of x plus h plus radical x. You would have noticed there was a problem similar to this on the diagnostic quiz, the very first quiz of the semester, except there wasn't a limit because you wouldn't have known about them yet. But this is kind of why that example was there. at this point we can plug in h equals 0, because as long as x is not 0, this will be a number, and we would end up with 1 over 2 radical x. Of course, we're assuming x is not 0 here. So this gives us another rule. The derivative of the square root function is 1 over 2 radical x. That's just something we know now. You could write this in terms of powers. It's not going to really matter, so you could think of this as that. And we're actually going to look at another rule where that would be the more natural way to think of it, but either way is fine. This is the slope of the square root function. That's what it will look like. For a familiar technique, multiplying and dividing by the conjugate. Let's change the function. Let's look at d. F of x equals 1 over x. So we want to find the derivative of the limit as h approaches 0 of f of x plus h minus f of x over h. So, applying this here, what does f of x plus h look like? 1 over x plus h, not separately. The x is replaced by x plus h, minus 1 over x, all over h. How do we take that limit? Yeah.
You
You can make it common denominator.
What would that be?
X times x plus h. And then the.
So we find that LCD, x times x plus h, multiply and divide by the LCD. That is the trick there. So if you take this times that, the x plus h is cancelled, you're left with an x. This times that, the x is cancelled, you're left with an x plus h. Be very careful here, this should be in parentheses. In the denominator, I would have hx times x plus h. Again, we never expand the denominator, I'm going to leave it like that. X would kill the x here. So this would be the limit as h approaches 0 of minus h, that's why the parentheses are important, over hx, x plus h. Realize the h's will cancel. This is the limit as h approaches 0 of minus 1 over x times x plus h. And at this point I can plug in h equals 0. And so that's just minus 1 over x squared. Again, we're assuming our x is not 0. Leading us to another rule. The derivative of the function 1 over x is minus 1 over x squared. Something worth memorizing, that function shows up often enough. Or, of course, you could write it in terms of powers, d dx of 1 over x, which you can think of as d dx of x to the minus 1. Well, that's just going to give you minus x to the minus 2. So not too bad there. So if you have to remember your algebra, you need to remember how to simplify complex fractions, how to simplify things with radicals in it, remember how to apply distributive law, and how to take limits in general. You need to be good at all that stuff to find derivatives this way. E should be interesting. sine function. F of x equals sine of x. So now we want to find the limit, the derivative via limits. So this implies f prime would equal to the limit as h approaches 0 of f of x plus h minus f of x over h. At this point, you should be tired of me writing that down. You should be like, oh my god, yes, okay, yeah. Hopefully. If every time I'm writing it down now you're guessing as to what comes next, that's a problem that you need to take care of. But you're supposed to be like, oh, we have to do this again. Okay, yeah, so we know. Which, by the way, is the trick. You need to start practicing until everything feels like that. See, when you're studying and you're like, I think I got it, you probably don't get it, right? You need to keep practicing to the point where, oh my god, you're just mindlessly going through the examples, getting everything right, and you have to be rolling your eyes. Why do I have to do this? That's the feeling you want to aim for. When you're there, you're ready. Before you get there, you're not ready. If you're like, yeah, I think I got it, I tried it, seems fine, seems understandable, seems simple enough, you don't understand. At that point, you don't understand yet. You understand when it's like, oh my god, this again, and it's just like going through the motions. That's the goal. Right? You should feel like you're writing down a definition when you're solving problems. Okay. What would that look like here? Yeah?
Sine of x plus h.
Of course, all of that is in the sign. Minus the original function, sine of x, all over h. Okay, how do we deal with that? What now? Kind of dark. Okay, now what? Yeah? What's next step? No, this one is the last example. Let's start using this side of the board. So what's the next step? Okay, how? Right. So remember the addition formula for the sine function. You need to know what is sine of a plus b, what is cosine of a plus b. That's called the addition formula for sine. You need to know the addition formulas, the double angle formulas, the half angle formulas, Pythagorean identities. Okay, so now that we have that, so trig functions don't distribute like, this is not sine of x plus sine of h, so that's very wrong. Sine of x plus h actually expands into something like this. What do we do now? Well, notice here, sine x is a common term between these two. So let's actually just put those together, see what happens. So put the sine x cosine h minus the sine x together, plus the cosine x sine h all over h. Now, two things, sine x is a common term here, but it's not here. So I'm going to split these into two parts. I'm going to factor out the common sign. Maybe that will lead to something nice. So this would be sine x times cosine h minus 1 over h plus cosine x times sine h over h. see anything? What can we do here? Yeah.
Cosine x sin h over h is equal to cosine x. Because the
Oh.
sin h over h.
Right, and that's now a special trig limit. Where sine of an angle over the angle as the angle is going to 0, that's like sine x over x as x is approaching 0, that is 1. So I know there is going to be a plus cosine in here. What about the first part? Yeah.
Cosine x minus 1.
Here is another special trig limit. That one we also know is 0. So we have 0 times the sine x, so that's just 0. In other words, the derivative of your sine function is cosine. Is the cosine function. The derivative of sine x is cosine of x. Similarly, we can show, I'm not going to do it, but we can show that the derivative of cosine is negative sine of x. Verification left to the reader. Okay, so do that. Try that, see if you can do it. Be good practice. So now we've seen how to find derivatives of some basic functions that will show up all the time, sine and cosine. You might be asking yourself, well, how do we differentiate the other trig functions? We will get to that. We actually need a little bit more robust machinery to talk about those without ripping our hair out, so we'll wait until we get some more theorems under our belt to be able to do that. But here's how you would break it down and find derivatives via the definition. So you plug into the limit definition and yeah, keep going. And of course, algebra is going to help a lot here in finding the limits. But other than that, if your algebra is solid, this will be straightforward. And pretty much everything I wrote in a box at this point, I just want you to remember it. That you kind of know by heart. You can find them by the definition if necessary, but otherwise you should kind of really just know those by heart. What else do I want to talk about today? Yes, finding things via limits can be a little bit annoying, so let's start making things a little bit easier. Let's talk about some algebraic properties of derivatives. How do derivatives behave under the algebraic operations? Addition, subtraction, multiplication, division, etc. Scalar multiplication. This is what we want to know. So let f and g be differentiable functions. Differentiable functions, remember the derivative is a limit. Limits might not exist. Calling a function differentiable means the limit definition, the derivative limit exists for these functions at all points on their domain. Derivative limit exists. So that means you can actually plug in the limit definition on these functions and it will make sense. Yes?
But does it need to be continuous, right?
Yes. But we'll talk about that later. We'll talk about the continuity properties at some other point. Something needs to be continuous in order for you to be able to differentiate. So now, let's say f and g are two differentiable functions. Let c be a constant. So let's look at one property. Suppose I wanted to find the derivative. So knowing that I can actually find the derivative of f, what is the derivative of a constant times f? So that's the first goal. This is, how does the derivative deal with scalar multiplication? If I take a function and multiply by a constant, how does the derivative behave? Well, we can actually use the definition here. This is actually going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. However, we can use the property of limits. We know that constants can actually factor outside of limits. So I can do that here. Just factor out the c. You'll notice here, this guy is just the derivative of f. So this is just c times the derivative of f. So we've learned a valuable property here. Constants can factor outside of derivatives. The derivative of a constant times a function is just a constant times the derivative of the function. This is called the constant factor rule. For derivatives. Basically says the derivative of a constant times a function is the constant times the derivative of the function. So that's an important thing to know. So in other words, if I have derivative of any of those guys that we looked at before, so like 5 square root of x, well that's just going to be 5 times the derivative of the square root of x, which is just going to be 5 divided by 2 radical x, for example. You kind of just leave the constant alone and multiply it after you take the derivative. And even this step, you don't really have to write this step. If you jump from here to here, I'll accept it. But I just want to rewrite it out so to emphasize the rule. You have a constant times a function. The derivative is just going to work on the variable part. The constant just hangs around. Because constants can be factored out. So that's one property of derivatives. They behave very nicely with constant multipliers. Let's look at another thing. Suppose I wanted to find the derivative of a sum of functions. Okay? So I know individually I can find the derivatives of f and g. If I take these two functions and add them together, does that affect the derivative in any way? Well, again, we can go by the definition. This is the limit as h approaches 0 of, everywhere I see an x, I replace with an x plus h, minus the original function, parentheses, very important. So this would be minus f minus g because of the distributive law. And similarly with the what we did when deriving sine, I'm just going to group like things together. So take the minus f, put it beside the f, take the minus g, put it beside the g. And now I can remember the rule that fractions actually distribute across the numerator. So if I have an addition in the top, I can actually split the fraction into 2 parts. There's a property of limits that say limits distribute across the sum. So the limit of this plus that is the limit of this plus the limit of that. And we've realized that that is just the difference quotient for f, and that is the difference quotient for g, and the denominators are approaching 0. This approaches the derivatives. So you would get f prime of x plus g prime of x. Nothing special about the addition sign here. Had I had a minus sign, it would have been very similar, leading to the following rule. It's called the sum difference rule for derivatives. this rule says to take the derivative of a sum of functions. It is just the sum of the derivatives of the functions. So derivatives distribute across sums. That's the takeaway here. Which is very special. Not everything distributes across a sum. Remember, powers don't distribute across sums, for example, but derivatives do. So if I have the derivative of a sum of functions, it's just the sum of the derivatives. I can actually take the derivative and distribute it, like a distributive law holds here. So, example, I can talk about what is the derivative of x squared, which we looked at last class, plus radical x minus 1 over x, just the third and 3. And you can think of it as, well, this you don't have to write, but I'm just going to illustrate here. You can think of it as the derivative of x squared plus the derivative of radical x plus minus the derivative of 1 over x. You can actually distribute that derivative operator. We saw last class that the derivative of x squared is 2x. The derivative of that we just saw is 1 over 2 radical x. The derivative of this is minus 1 over x squared times that minus plus 1 over x squared. So that would be the derivative of that function. You should also know we can apply 1 and 2 together. So an example here, I could have the derivative of 5x squared minus 2 sine x plus 5 over x. And by the sum rule, I can think of this as the derivative of each individual function, and then the constants in front, by the constant factor rule, I can factor those off. So you can think of this as 5 times the derivative of the x squared minus 2 times the derivative of the sine plus 5 times the derivative of 1 over x. Again, you don't have to write it, but I just wanted you to show how is it being applied. But you can just leave the 5 alone, differentiate the x squared, that will give you 2x, ultimately you get 10x here. Leave the minus 2 alone, differentiate the sine function, gives you a cosine, you get minus 2 cosine. Leave the 5 alone, differentiate the 1 over x, get minus 5 over x squared. And that would be that derivative. So derivatives distribute across sums, and constant factors can be factored out. You essentially ignore them until the end. So if you know how to differentiate individual functions, you can differentiate combinations of these. Now you might ask, what about products? What if I had a function times another function? Is that just, I don't want to find the derivative. So if I wanted the derivative of this, is that just the derivatives of the individuals multiplied together? You could ask about, what about quotients? You could ask the question, if I'm taking the derivative of a division, f divided by g, what is that? Is that just, does it just distribute? Short answer is no. The long answer is, we'll prove things next class where we'll be able to prove that the answer is no. So it turns out derivatives do not play well with multiplication and division. So stay tuned. By the end of the next class, we'll have enough machinery to actually show how, not only that the derivative doesn't behave in a natural way here, but we'll be able to tell exactly how it would behave in these cases. For sums and scalar multiples though, it behaves very naturally. Distributive law applies and factoring out applies. We're talking about multiplication of two functions that have just variables in them. It's a little bit trickier than that. So right now, I just want you to get those big ideas. Know how to find derivatives of individual functions. Given that you know them, you also automatically know how to find the derivatives of any constant times those functions. You automatically know how to find the derivative of a sum or difference of any of those functions. And you automatically know how to find the derivative of constant times each term of sums of those functions. So the algebra that derivatives of A allows to find derivatives of more and more complicated things without having to go through an entire limit definition all over again. What else do I want to talk about? Okay, so I'm going to talk about one rule, kind of more sophisticated here, but we're going to use it on Friday to derive a lot of important things. It's a very important rule. It's not at all easy to prove, so we're not going to prove it, so I'm just going to tell you, you're going to take it on faith. If you care to look at the proof, you can look it up yourself, read it. If you understand it, it's great. You need a really good understanding of limits to see why this rule would work. There are simple proofs out there, but they're usually wrong. It's a real proof that deals with it in all its subtleness and complexity is kind of above a Calc 1 class pay grade. It's called the chain rule. So this is a rule that allows us to differentiate under another very particular algebraic operation, the composition. So we use this to differentiate composite functions. Remember what composite functions are? So when you take a function, you plug it inside another function. It's called this is called function composition, and it's called the composite function. So chain rule says a bunch of stuff. Okay, let f and g be differentiable and g be g of x be in the domain f, then we can differentiate the function f of g of x. So I can take one function and plug it inside of another function. And I can find the derivative of that new function by doing this equals. It's the derivative of the f, or the outer function, leaving the inside one alone, multiplied by the derivative of the inner function. So that's one way you can think about it. Derivative of the outside function multiplied by the derivative of the inside function. So this is derivative of outer function you leave the inner function alone. Sometimes students forget that. Initially, you leave the inner function alone, and then you multiply by the derivative of the inside function. Let me give you an example here. We'll talk more about this because we're actually going to use it to derive some cool things. But to give you one simple example, suppose I wanted to differentiate the following. find the derivative of sine of x squared plus radical x. Now, you should immediately strike it as something different from just the sine of x function. Okay? We don't just have sine of x, we have sine of an entire function. And one way you can dissect this in your head is to realize that, well, I can take f equals sine x to be the outer function. And I can take g equals x squared plus square root of x to be the inner function. And basically you'll realize that to create this function, what you actually did was you took this guy and you plugged it inside of this guy. Right? So this guy's on the outside, this guy goes inside that one. Right? So here's your inner function, and your sine happens to be the outer function. Now we can talk about how do you differentiate something like that? Well, you would follow this rule. You would differentiate the outer function, leaving the inside intact, and then you would multiply by the derivative of the inner function. And in doing so, you say you've done the chain rule. So let's actually do that. So this is equal to, so your outer function is the sine. What's the derivative of that?
Cosine.
So it's just cosine, right? Which we've shown just now. So this is the outside function. Find its derivative. Now, in the meantime, you leave the inside alone. Don't do anything with that. Then you're going to multiply that by the derivative of the inside function. And what's that going to be? Yeah?
2x plus 1 over 2x.
Very important that you know that there should be parentheses here. Because distributive law is still a thing, you'd have to take the cosine times 2x plus the cosine times that if you wanted to flesh these out. So you do need the parentheses here. But ultimately, that would be your derivative. So here you had a function x squared plus radical x plugged inside of the sine function. If someone asks you, what's the slope of that function? Well, to differentiate the outside, leave the inside alone, and then multiply by the derivative of the inside afterwards. Doing that is called the chain rule. And that pretty much wraps up our time. Next time, we'll actually mention this again, but use it to actually derive something. And hopefully, do some nice examples after that. I have quizzes to give back, so you can grab these as you're leaving.